Fifth speaker, halfway through, is Joe. Now, how Joe. 3 minutes. 3, 2. Just joking. 3, 2, 1, go.
My PhD is on the optical spectroscopy of extreme nanowires, which is just a fancy way of saying I look at really small things. But when I say small, I mean very small, because I work on the nanoscale, which is a billionth of a metre. To put that in a bit of perspective, it's about the distance that a frigate will sink if a seagull lands on it. So incredibly small scale work. And why is this nanoscale interesting for us then? Well, there's an increased demand in society for higher, better performing electronics, mobile phones, etc. that have reduced power consumption. And scientists meet this demand by reducing the size of the things that we sort of squeeze into the phones. If you make them smaller, you can put more in, and make the phones and technology better. My work is extreme in the sense that I operate at the fundamental limit of the nanoscale. It's literally impossible to go any smaller than 1 or 2 atoms across, which is incredibly small. Bearing in mind the current record for such technology lies at around 10 to 20 nanometers. This is orders of magnitude smaller still. So why is this interesting exactly? Why do I do it? Well, I do it by filling carbon nanotubes. A carbon nanotube is essentially a cylinder or straw made of carbon atoms, just 1 or 2 nanometers across. And I get some material that I want to make into a nanowire, and I get some carbon nanotubes, and I grind the two things together in a pestle and mortar, and I just bake it in the oven for about 8 hours, for 800 degrees, or gas mark 20 if you want to do that. This material melts down, fills the inside of the nanotube, and when I take it out of the oven, it recrystallizes. The atoms bond together and form this extreme nanowire structure. I then use a method known as Raman spectroscopy, which is a method of probing vibrational and electronic states of the material to understand the properties of that I'm interested in. I use a laser, which excites electrons in atoms to higher energy states. These electrons then scatter off vibrations in the material, releasing another photon in the process. When I measure this output photon and compare it to the input, I get an idea about the kind of vibrational energy involved, which in turn tells me information about our material. It's kind of like if you were to flick a piece of glass or wood or metal, you'd be able to tell the difference based on the sounds that they make and deduce properties on the material from that. Except in this case, I flick it with a laser, and the sound I listen to is a vibrational Raman spectrum. But the principle is still the same. So, what have I discovered so far then? Well, so far I found that I can fill a whole host of materials inside carbon nanotubes. And I found by doing so, the atoms of these materials bond very differently than they would in the large scale or unconfined case. These new allotropes that I create are very different from their bulk equivalent. They behave completely differently. There's new physics at this sort of level that we have yet to understand. And it's important that we want to understand this, because this really is the fundamental limit of nanoscale, and it could be where technology is sort of heading for in the future. So we need to understand the physics of the nanoscale to really understand how low we can go with nano. Thank you.